Hello everyone, and welcome back to Science on E-Learning. Yay! So in the past two classes we talked about wind, how it's created, and also how wind turbines work. Now, I want us to look at wind turbine design. How do we build them in order to capture the wind's kinetic energy and generate electricity? Now, the goal is that when we get back to school, whenever that is, we will build wind turbines in class and test them to see who can generate the most electricity. So please pay close attention and think about how you can design a wind turbine in order to make the most electricity. Our objectives here for today: what aerodynamic properties are important, and describe the importance of blade design. Excuse me. So, first of all, vocabulary. Aerodynamics. Again, aerodynamics. Aerodynamics are the properties of a solid object and how it interacts with the wind. Okay? Like this. Funny example, but good nonetheless. A cow is a solid object, and we see how it interacts with the wind. The wind is moving over it. The yellow is increased pressure as it moves over the top and under the bottom of the cow. And then you see the green parts of the wind are the speed of it. Okay, so a little cute example there. Next, an anemometer determines which way the wind is blowing. So you might see an anemometer on a wind turbine or other things for that matter. Usually those little cup-like features that spin. Now let's think here quickly about aerodynamic properties. Okay? The shape and design of a wind turbine will determine its efficiency. All right? How much energy can we capture from the wind and convert it or change it into electricity? This will be determined by the design. As we know, where there is motion, wind is air in motion, there is kinetic energy. And wind turbines present an obstacle, okay, present something to capture that kinetic energy. Okay, think about our last lesson, all right? If somebody throws you a ball, that moving ball has kinetic energy. And when you catch the ball, your hands present an obstacle, all right? That obstacle is stopping the ball. In this example, the wind turbine is the obstacle stopping or capturing the kinetic energy of the wind. Now there are a variety of designs which we're going to look at, okay? But the idea here, and wait till this GIF restarts, is that the blade is going to capture the wind. Okay, we're going to look at this in a little bit, but you see how the wind is moving over and under this blade. Okay? Looks like an airplane wing. And for good reason. An airplane wing works in a similar fashion to a wind turbine blade. Okay, we'll come back to this. So, wind, kinetic energy, motion energy, moving energy. This wind puts pressure on the blade as it hits it. The more surface area, aka the larger or the bigger an area the wind hits, the slower the air will travel and the more pressure will be applied to the blade. Okay? So again, the bigger the surface area, the more area the wind has to hit, slow, and apply pressure. Now this pressure will cause lift, and this lift causes the blade to turn or move or spin. Okay? And like I alluded to, this is how the wings of an airplane work. Okay? The wind is putting pressure on the airplane wing, lifting it. So let's think about that here. All right? So you can either think about an airplane wing or a wind turbine blade. Okay? The same principle applies to both. You've got the blade here in this example, or the airplane wing, let's say, and you see the wind moving over the blade. Now, above the blade, the air is moving faster, right? And it's creating lower pressure. The wind below the blade is moving slower, and it's applying pressure. It's high pressure being applied to the blade, pushing that blade. And as that slower air, or that high pressure, pushes the blade, it creates lift. Just like that example we looked at before. The wind is moving over the blade, and you see the wind above the blade is moving faster. It looks wispy at the end, all right, breaking up, moving quickly. Whereas the air moving below the blade, you see those lines getting compressed, all right? And it's pushing against the blade, applying pressure, and creating lift as it moves slowly below the blade. Okay? So these are the aerodynamic properties we need to understand and consider when it comes to blade design, or if you're just interested, maybe an airplane, okay? It's a good way to think about this concept. Now, knowing what we know about how aerodynamics work, how wind presses against a blade, causing lift, causing things to spin. Let's look at blade design. So, the amount, the size, and design of the blades will determine how powerful and effective this wind turbine is at turning wind energy into electrical energy. Again, we've got a couple different designs, different concepts. So, as we're going forward here, think about this. Think to yourself, if I wanted to design a blade to create electricity, which we will do in class, what is going to be the best design? Or, what do you think would be interesting to build? I want you to use your imagination, but also these scientific concepts to make an effective design, okay? So, a wind turbine with more blades will be more powerful, but less efficient. So it's going to have more power, but it's going to be less efficient or effective at turning that kinetic energy of the wind into electricity. Longer blades will increase the turbine's diameter and allow it to capture more wind than a turbine with shorter blades. Now, let's look at the picture on the right. All right, we've got the turbine there, and you see if we draw a circle, all right, using the tips or the ends of the turbine blade, we make a big circle, and the diameter is measuring the turbine blades, or that circle, from one side to the other. So again, the bigger the diameter of the blades, the easier it will be to capture wind and turn that into electricity. So you see the example on the right, you've got small blades which continually get bigger and bigger and bigger and bigger. And you see how the kilowatts, all right, the energy or the electricity, let's say, being generated increases from 75 to 300, 750, 1,500, 1,800, 3,000 kilowatts at the end with a 100-meter diameter blade. Again here, what we've got is a chart showing that as rotor diameter, or blade diameter, let's say, increases, so does the power output. So that blue dotted-ish line is the diameter, the meters, how wide it is, and the black dotted line of sorts is the power output. How many megawatts are being created or generated by those bigger diameter blades. Now, additionally, if we curve the blades of a wind turbine, all right, twist them a little bit, let's say, it allows us to capture 5 to 10% more wind energy. So we've got the blades, they are working, they're capturing the energy, but if we just curve the blades a little bit, we can generate 5 to 10% more energy. Okay? Or capture 5 to 10% more wind energy, which allows us to make our turbine more efficient and generate more electricity. Critical information. Now, as we saw before, we've got some different designs. First one is just one blade. So this blade, or just one blade turbine, is optimal, and it would provide the most energy for us. But the blade and the turbine would be unbalanced. Now, you may wonder, well, what does that matter? Well, we have to think about the structural integrity of the entire turbine. If the blade spinning in high winds causes an imbalance, causes it to be unbalanced, it could damage or break the turbine or the tower. So if we have the potential to break the tower or the turbine, it's not exactly a good design, even though it's going to provide us the most energy. Similarly, with two blades. Now, two blades would produce more energy than three blades, but it would produce less energy than one blade. However, this too would be unbalanced. Okay, again, we're thinking about the structural integrity of the entire turbine. If it's unbalanced, it could break the turbine, it could break the tower, and be useless. So, we get to 3-blade turbine designs. Now, as you can probably guess, 3 blades would produce less energy than 1 or 2-blade turbines, but guess what? It's the best. It's the best because it doesn't have the problems of the other two. All right? Namely, it's not unbalanced. Okay? So here we are preserving the structural integrity of the whole turbine and at the same time creating a good amount of energy. Now with these, the one thing is each blade must be 120 degrees apart. Now, you can guess, all right, if we have each at 120 degrees, it forms a full circle, all right? They're equal distance apart, okay? We know 360 degrees, form a circle, divide that by 3, we get 120 degrees. Now, we could design a blade with a turbine with 4 or more blades. Now, these would produce the least amount of energy because the blades would produce too much resistance. So, what do I mean by that? I mean, as the blades spin, they're going to almost slow each other down by capturing the energy of the wind, disproportionately. Okay, so it'll work, it'll create and generate energy, but it's not going to be as efficient or effective as 3 blades. So I want you to think about this. Now, when we, and if we get to build our wind turbines, you are free to do whatever you want. If you want to make a 1-blade design, go for it. 2 blades, great. 3 blades, wonderful. If you want to do 4 or 5 or 6, that's up to you, okay? Whatever you think is the best, as long as it's generating electricity and is doing the job, guess what? You have design something that works. So we'll look at this and think about this in class. So again, we went over what aerodynamic properties are important, and we described the importance of blade design. Again, like I just said, the goal is that we will build this in class and hopefully generate some electricity, have a little fun, get to work and think and design and explore on our own as independent people, and see how well we do. So I know this was a long class, ladies, but please make sure you complete the worksheet. Please complete the attendance questions. Next class, we'll kind of be flip-flopping a little bit, going back to another topic, and then moving forward from there. Again, with e-learning and the situation, we've got to take it day by day. So, thank you and have a lovely day.